Hello everyone, welcome to the second lecture of this module where we are discussing characteristics of sensors. The course is Microsensors and Nanosensors. In the first module, we have covered the introduction and different classes of sensors. In the previous class, we have discussed some of the characteristics. We have classified them under static characteristics. So in today's class also, we will continue our discussion on static characteristics. In previous class, we have covered span, full-scale output and calibration. We have also seen calibration error. Now, let us discuss hysteresis. You have came across this particular word when you have studied about magnetic material. Okay, so you have a curve between flux density and magnetic force where you actually see the hysteresis curve. Okay, so for magnetic material it is good, hysteresis is desirable. Okay, however, we'll see now that hysteresis is not desirable in case of microsensors and nanosensors. Okay, so hysteresis is defined as a deviation in the output when you have stimulus applied from increasing to decreasing sequence and then from increasing to decreasing sequence. Okay, so it is the deviation from sensor's output at a given input when input is approached from the opposite direction. When I say opposite direction, I mean to say that from increase or from highest point to lowest. Okay, so first you have increase from the stimulus, or say it can be some analyte if it is a gas sensor or a chemical sensor. Okay, it can be some pressure, it can be some force. Okay, depending on what sensor we are discussing. Okay, so you keep on increasing the stimulus, okay, the quantity of the stimulus, and then you decrease. Okay, this value, the maximum value, is known as hysteresis. Okay, so it is the non-coincidence between the loading and unloading curve. Okay, and maximum input hysteresis, as you can see here, okay, is mostly denoted in the percentage of full scale input. Okay, examples can be spring-based instrument, direction-dependent frictional instruments, magnetic field-based instruments, and all. Okay, so hysteresis is the maximum difference in the output when the value is approached with an increase or decrease in concentration of the analyte. Okay, so consider this example of a two-terminal device. Okay, again this is we are taking example of gas sensor. So say this is a gas sensor. Okay, let's see its dynamic curve for a fictitious sensor. Okay, say this is a hydrogen sensor, for example. Okay, and I'm plotting this this response in terms of, say, this is giving some result in terms of current, and say this is a current versus time curve for different input. Okay, different concentration. Okay, so say this is a material, this is device which is based on a material whose conductivity increases with the analyte. Okay, so here I have so this was my baseline resistance or baseline current. Okay, so consider this curve. This is the response, dynamic response of the sensor. I have current versus time. Okay, this is my baseline current. Okay, here I have introduced my analyte. Say here it is hydrogen. Okay, the current has increased because the sensing material is such that its conductivity will increase with the introduction of gas molecule. Okay, now say this go on increasing. Okay, now say here I have exposed it to 100 ppm. Say this is 150 ppm. This is say 200 ppm. Okay, now I know that my device has entered into saturation. Okay, so now I started bringing the concentration low. Okay, so now I have say this is my another response of 150 ppm and another response at 100 ppm. All right, so I have data from increasing concentration of hydrogen from 100 to 200, say 100, 150 and 200, and then going back from 200 to 100. So 200, 150 and 100 ppm. Say here the current is I1, here the current value is I2, this is I3, this is I4, and this is I5, while the baseline current is I0. Okay, this is my dynamic response. Now let us plot a static data for this particular dynamic response. Okay, if I plot this, the plot will be between current, okay, say it is in milliamp, and concentration, say it is in ppm of hydrogen. Okay, now say while increasing, it went from say 100, say this is 100, this is 150, and this is around 200. Okay, so the response increased from 100 to 200, and these currents are I1, I2 and I3. Now what I am doing is I am now decreasing the concentration of hydrogen. Okay, say I4 is coming somewhere here, while I5 is somewhere here. Okay, so when I decrease the concentration, I have a plot something like this. Okay, and from this static curve I can find the hysteresis, which is the maximum difference in the output when the value is approached with an increase or decrease in concentration. So my hysteresis will be somewhere here between two currents, okay, at the same instance. Okay, I hope this concept of hysteresis is clear to you. Okay, typical cause of hysteresis in a device or in a sensor is mostly the geometry of the design, the friction if it is a mechanical sensor, structural change in the material. Okay, the receptor material changes its structure. Okay, particularly in case of mesoporous and microporous material, this has been observed. Okay, there can be other reasons also, like in this case, say if hydrogen is chemi-jobbed at the sensor's surface. Okay, you know that sensing is a surface phenomena. So if some hydrogen molecule, say when it is exposed to 200 ppm, which is typically a high concentration, some of the hydrogen molecule is attached to the sensor material surface. Okay, now automatically the conductivity is at higher state when the another concentration of say 150 ppm is introduced. Okay, so already it has some level of increased conductivity, and now you are pushing another 150 ppm of concentration. Okay, therefore the current level will be obviously at higher side. All right, therefore it can also be due to permanent change in or pseudo permanent change in the surface of the sensing material. Okay, so let's move towards next characteristic, which is linearity and non-linearity. Okay, mostly this linearity is defined in terms of non-linearity only. Okay, so non-linearity of a sensor is the maximum deviation of output from a straight line. Okay, it is usually expressed as the percentage of full scale reading. So maximum deviation of the output from the ideal straight line divided by full scale deflection into 100 gives you a non-linearity in the sensor's response in percentage. You can see here transfer function where the output is plotted versus the measured value of the analyte. Okay, you can see this cross edge shows the actual response. Okay, now what you have to find is the maximum deviation from the straight line which has been drawn over here. Okay, this divided by the full scale deflection of the sensor. When you multiply it with 100, it gives you non-linearity of the device in percentage. Okay, so I hope that non-linearity is clear. Next, move to saturation. Okay, saturation is very crucial to a sensor. And if you understand this saturation, even if you are an end user, you may be able to save your sensor and you may use it for longer time. Okay, so before we actually use a sensor, we should understand that every sensor has its operational limits. Okay, so every sensor comes with some specification sheet. Okay, and there the manufacturer usually mention the operating limits. Okay, so if it is a pressure sensor, they will mention that, okay, this sensor can work in this particular range of pressure. Similarly, for force sensor, they will mention some range of micronewton. For chemical sensor or a gas sensor, they mention some particular concentration in terms of ppm, or in some other concentration unit for the sensor to operate. Okay. We should always follow the instruction of the manufacturer, and we should always use the sensors in that particular range. Okay, and that is mostly to avoid saturation of the device. Once it reaches saturation, you may need to recalibrate the sensor. And in the previous class, we have already seen that calibration is sometimes very tricky, particularly for multi-point fitting. It becomes very tedious job. Okay. So saturation is something which nearly all the sensors has to achieve. Okay. So if your sensor's transfer function is linear, do not think that the sensor's response will be linear only beyond the dynamic range. Okay. It may be non-linear, it may be saturating, we never know. Okay, so even in linear sensors, at some level of input stimuli, its output signal will no longer be responsive. Okay, you will not have the correct output, or even the sensor may be non-responsive. Okay, further increase in stimulus do not produce a desirable output. Okay, you may have some erroneous result if you keep on increasing the stimulus value. Okay, it is said that the sensor exhibit a span end non-linearity or saturation. Okay, so even for a linear sensor, in the saturation region you have a non-linearity. We call it span end non-linearity, as you can see in the on the screen where the transfer function of the sensor is plotted, and I have a very linear span. Okay, however, the non-linearity is introduced at the end of the span, and we call it span end non-linearity or saturation. So if my device is or my sensor is working in this particular range of stimuli, I will say that, okay, my device is operating in the dynamic range. Okay, and if it is going beyond, I should say that my device has entered into the saturation. Okay, and if the data is very crucial, I cannot rely on the reading if the sensor is working in the saturation region. Okay, so the correct reason for the operation for the device is the linear span. Okay, next is stability. We'll come across stability once again when we will discuss the effect of environment, but let us discuss this in very brief. Okay, it is the ability of a sensor to produce reproducible results for a certain period of time. Okay, this includes retaining the sensitivity, selectivity, response and recovery time, and other parameters of a sensor. Okay, so sometimes it is very tedious to find the sensitivity, selectivity, response and recovery time, and all those things every time. Okay, so sometime what we do is we just find that if the baseline is correct or not. Okay, say if I have a sensor, okay, I am exposing it to some analyte. Okay, but say if the analyte is absent for multiple days, okay, or multiple number of hours. Okay, if in that case the baseline current or baseline resistance or baseline voltage is giving the correct value, say at time equal to 0, I have found that a current I naught is flowing in the device or flowing in the sensor, which is my baseline current. Okay, if at time equal to t1, say t2, or time equal to t3, okay, if it is retaining this baseline current, okay, this t1, t2, t3 can be even a larger value in terms of some few tens of hours also. Okay, and if this value, this I naught is retained by the sensor. Okay, so I naught is not deviating say beyond plus minus say 0.01% or say plus minus 0.005% or so. Okay, I can say that my device performance or my sensor's performance will be stable. Okay, of course I can say more correctly when I find its sensitivity, selectivity and other values over the time, okay. But by seeing the stable baseline current in a stable devices, I can say that this device will have better stability, okay. We'll come to stability once more when we will discuss the environment factors, okay. Another important characteristic or static characteristic of a sensor is repeatability, okay. It is the ability of a sensor to show a certain response value when subjected to certain concentration of analyte, okay. This is how we define the repeatability of a sensor, okay. Now let us consider that in this curve, this is again a characteristic curve of a sensor where I have plotted the current versus time with same concentration applied to the sensor multiple times, okay. I call it, say, cycle 1, this is cycle 2, cycle 3, cycle 4. One cycle constitute a application subjecting the sensor to some analyte, say x ppm of some curve, some gas, okay. Now this sensor has a characteristic where the resistivity increases with the introduction of the analyte, okay. So the resistance of the device is changing when you are subjecting it to some gas, say a gas Y, okay. Now one cycle constitute applying this concentration or subjecting this sensor or exposing this sensor to concentration X of that particular gas, okay. Closing this concentration, so at this particular point I have switched off this X to 0. So at this particular point in this curve, X has become 0, okay. Now I have given time to this device to come back to its original state somewhere here, okay. So this introduction, making it 0, exposure to X, making this value X to 0, and then allowing this sensor to recover its own and reaching this value of baseline, okay. This is making a cycle and I am calling this one cycle. So this is cycle 1, this is cycle 2, this is my cycle 3, this is my cycle 4, okay. Similarly, I can have multiple cycle of this introducing the analyte, okay, then making it 0 and allowing the sensor to come back to its original position, okay. I can allow this multiple times, okay. And if you see, these values and the baseline values are similar, okay. I can say that my sensor's response is repeatable, okay. Now there can be cases where this is not achievable, okay. Let us see one characteristic curve where the response is non-repeatable, okay. All right. Now consider another sensor A where a gas B is introduced in, say, the concentration is, say, Z, okay, or Z1. Z1 concentration has been introduced here, or the sensor has been exposed to Z1 concentration of this gas, okay. And this is, say, initial voltage, okay. Now this is a device where I am giving a constant current bias, okay, and the voltage change is being measured, okay. Now say this is V naught, okay. Say for this concentration, when I am exposing it to concentration Z1, this V naught is increased to V1, okay. Ideally, when I am switching it off, okay, I am making this Z1 as 0, similar to the previous case, okay, this should come back to the original baseline voltage, which is V naught, okay, which is not happening over here. Now, this is coming to be some V naught plus delta V naught, okay. This is the change of the baseline which this device has retained, okay. Now, if you see, when I am exposing it to another concentration Z2, this Z2 is say little bit higher than Z1, okay. Say Z1 is if 100 ppm, Z2 is say 150 ppm or so, okay. The scenario becomes even worse, okay. Say this difference was del V, V naught, okay. Now, the difference has further increased, say this is 5 del V naught, okay. Now, the new baseline has become something like V naught plus 5 delta V naught, 5 delta V naught, okay. The baseline is shifting and there can be a number of reasons for this baseline drift, okay. In this case, I can say that performance of my device is poorer and it is not repeatable, okay. Usually, we should find out in practical sense that what is the cause of this non-repeatability, okay, and we should try to rectify it. With repeatability, there is another term, reproducibility, okay. Reproducibility of the sensor is even done for longer time and at different places, okay. So, if my sensor has a response of say 70% for a concentration of say x ppm in a city of India where the humidity was 60% RH, okay. Now, if I will test this device in another city where the relative humidity is very, very high, say it is 98%, okay, a reproducible sensor may retain this response to 70%, okay, because it may have some minimal effect from ambient factors, okay, for again for x ppm only, okay. However, if it decreases to say 50% or if it goes to say 90%, okay, I can say that the results are not reproducible, okay. So, these are two concepts of repeatability and reproducibility of a sensor. A good sensor will have better repeatability and very good reproducibility. With repeatability, we have another terminology which is repeatability error, okay. It is caused by the inability of a sensor to represent the same value under presumably identical conditions, okay, as you have seen with the example of cycle 1, cycle 2 and cycle 3, okay. Say this is one of the example where the error is represented by some plus minus values, okay. The repeatability is expressed as a maximum difference between the output reading as determined by two calibrating cycles unless and otherwise specified, and it can be written in terms of full scale reading as this difference that I have just talked about divided by full scale reading into 100, okay. There can be various source of repeatability error, okay, particularly thermal noise. We will discuss this noise very soon in detail, okay. Then build up charges, materials plasticity, okay, particularly for mechanical sensors, force sensor, pressure sensor and all, this plasticity plays very important role, okay, and it may hamper the repeatability of the device, okay. So, these can be some of the sources of the repeatability error, okay. So, now we know what is repeatability, reproducibility and reproducibility error, okay, or repeatability error. So, with this I am stopping this lecture here. We will discuss some more static characteristics in the next lecture. We will also try to discuss some of the noise in these microsensors and nanosensors because they are very crucial for its better performance. Thank you.